Section 6.1 Systems of Equations. In this section we're going to take a look at how to solve systems of equations. So let's get started. So first of all we need to define what is a system of equations. So a system of equations is a collection of equations in more than one variable. Okay, so it's a collection of equations in more than one variable. Up to this point in this class, we've only dealt with one equation and one unknown, or maybe one equation and two or three unknowns, but we only had one equation. Now we're going to have more than one equation and more than one unknown and more than one variable. So here's a quick example. So let's say I have a system like this. I have x plus 2y is equal to 3. I have 4x plus 5y is equal to 6. This is a system. Okay, it is made up of two equations and it has two unknowns, x and y. Okay, so now when we solve a system, unlike solving an equation, when we have only one equation, what are we trying to do? We are trying to find the value of that variable for which the equation is true. That means the two sides of the equation are the same. Now not only are we trying to find the value of the variables, we have more than one, for which not just one equation is true, but all of the equations in the system are true. So not only do we want to satisfy one equation, we want to satisfy all of them. Like for example, in this case, just to illustrate a point, okay, if I say x is 1 and y is 1, okay, that satisfies this equation. If x is 1, y is 1, we get 1 plus 2 times 1 is 2, so 1 plus 2 is 3. So that satisfies this one. But how about this one? If x is 1, we get 4, and if y is 1, we get 5. 4 plus 5 is 9. It doesn't satisfy this one. So this is not a solution to this system. Okay, so we are looking for values of x and y that satisfy both the equations, not just one. So that's what's special about systems. We are no longer interested in just satisfying one equation, but we're interested in satisfying a collection of equations. Okay, and in this section we're mainly going to be interested in a system that's made up of two equations and two unknowns. That's why I've written down 2 by 2. Okay, so that's why we have a 2 by 2. That's what we call a 2 by 2 system. In the next section we'll take a look at a 3 by 3 system where we have 3 equations, 3 unknowns, or 4 equations and 4 unknowns, and so on. But in this section we're going to focus on a 2 by 2 system. Okay, now before we go any further, let me just learn how to solve them. Let me go ahead and talk about this first equation. This first equation has two variables and the degree of each of these variables is 1. So that tells me that this is an equation of a line. Okay, so let's go ahead and graph it first. For the sake of argument, I don't know what it looks like and I'll graph it later, but for now let's say this is the graph of that first line. So what does that mean? Every point on this line satisfies this equation. For example, this 1, 1 would be one of the points on this line. Okay, because this value of x and this value of y satisfies this equation. So every point on this line satisfies this particular equation. Now if I were to graph the second line, it might look like this. Okay, that means every point on this line satisfies this equation. Okay, so now what are we looking for? Okay, if all the points on the first line satisfy the first equation and all the points on the second line satisfy the second equation, what are we looking for? We are looking for points that satisfy both of them, right? In this case, there's only going to be one point that satisfies both of them. That's this point, because this point lives on the first line and also on the second line. That means it satisfies the first equation and also the second equation. Okay, so this would be the solution to this system. Okay, and since when we talk about systems, okay, mainly we are talking about linear systems out here, that's why they are lines. Okay, when we talk about systems like this, okay, our solution will always be points of intersection. So we always want to write a solution as a point because we're looking for a point of intersection. We're looking for a point that satisfies both of them. Okay, so I hope you understand what we mean by a system. A system is a collection of equations, okay, in more than one unknown, and a solution to a system is a point. So let's write that down. A solution to a system R, and I'm using the word R for a reason, because I'm going to put points with an S here, because there could be more than one point, and I'll explain that later. Are points that satisfy both the equations in the system. Not just one, but both. Okay, and I hope I convinced you that we are actually looking for points of intersection of lines, because in this section we are looking at mainly linear systems. So the title of the section should have been systems of linear equations. Okay, so let's do that. Linear equations. Okay, linear means degree 1, so the graphs of those would be line. So now that we have an idea what a system is and what we mean by a solution, okay, so let's go ahead and take a look at how to solve a system. Solving a system. Okay, there's many different ways to solve a system depending upon what type of system we have. In this section we're going to have mainly 2x2 systems. Okay, so for a 2x2 system, these are the methods we can use to solve. Okay, so the first method is graphing, because we can graph the two lines and we can find the points of intersection by looking at the graphs. The second way to solve is by substitution. Okay. The third way to solve is by elimination. Okay, so these three methods we can use. Actually, there's one more, I'm sorry. Cramer's rule. And there's one more, matrix elimination. Now I can solve a 2x2 system using any of these methods. Okay, so we can solve a 2x2 system using any of these methods. Okay, but I do want to stress this. The matrix elimination is mainly used for 3x3 and higher systems. So 4x4, 5x5, 6x6, and so on, where you have more unknowns and more equations. That's where matrix elimination is really good for. But I can still use it to solve a 2x2. Okay, so these are all the methods that are there to solve a system. In this section, we're going to take a look at the first three. Okay, in 6.1, we're going to take a look at matrix elimination in 6.2, and then we'll take a look at Cramer's rule in 6.3. Okay, so we're going to take a look at each method separate in different sections, but out here we're going to take a look at this collection because they're fairly straightforward, and they're mainly used for 2x2, because we always use the first three methods for 2x2. That's why they're in one section. Okay, so let's get started. So the first method that we're going to take a look at is graphing. Okay, so basically all we want to do is graph the lines and find the point of intersection. So you graph the two lines and find the point of intersection. Okay, and right away you should be able to tell, okay, this is not going to be good, because what if my point of intersection is a repeating decimal, 1.33333? I'm not going to be able to graph that accurately unless I truncate it, unless I chop it off somewhere. So it's really, really difficult to solve a system by graphing. Unless your equations are really nice, it's going to be pretty much impossible to solve a system by graphing. But it is a great place to start, because it teaches you a little bit about the system, because it tells you a system of linear, particularly linear equation in two variables, is basically just a collection of lines that you're graphing, and then you're trying to find the points of intersection of those lines. Okay, so let's take a look at an example. Let's say I have this system. I'm going to use this example for all the methods. So okay, x plus 2y is equal to 3, and we have 4x plus 5y is equal to 6. So this is my first equation. This is my second equation. Okay, so I want to find the solution to this equation. Okay, and we already agreed a solution to an equation is a point. Okay, especially to systems is always a point. Solution to a system of linear equation is always a point. Okay, so let's do that. Alright, so to graph a line, there's many different ways. We only need 2 points, and there's many different ways to find those 2 points. You can pick 2 random values of x and then find the 2 corresponding values of y, and you get 2 points on the line that you can connect. Or you can find the x and the y intercepts, that'll give you 2 points on the line that you can connect. Or you can use the y-intercept and the slope of the line to find the second point, and then you can connect those 2 points to draw the line. So there's many different ways to draw the line. And if you followed along with this class, you know I prefer x and the y-intercepts to graph a line. So I'm going to do that. So I'm going to graph for the first line, I'm going to find the x and the y-intercepts. To find the x-intercept, what do? We set y to 0. So I get x is equal to 3 if this y is 0. And to find the y-intercept, what do? We set x to 0. So we get 2y is equal to 3. So we get y is equal to 3 halves. Okay, so my x-intercept is 3, 0, and my y-intercept is 0 and 3 halves. So I found my x and the y-intercepts. Okay, now I'm going to do the same thing for the second line, then we'll plot all of them together. To find the x-intercept, we set y to 0, so we get 4x is equal to 6 because y is 0. So we get 4x is equal to 6. You divide by 4. So we end up with 3 halves. So my x-intercept over here is 3 halves and 0, or 1.5. Okay, and to find the y-intercept, what do? We set x to 0, so we get 5y is equal to 6. So I get y is equal to 6 fifths. So I get 0 and 6 fifths. So I found my x and the y-intercept. So let's go ahead and graph these lines. Okay. Okay, so I have 1, 2, and you can see you have to be very accurate with your scaling, with your drawing, whenever you use graphing to solve a system, and that's really hard to do by hand. On computers it's easy, but by hand it's really hard to do. So let's graph the first line. The x-intercept is 3, 0, that's this point. The y-intercept is 0 and 3 halves, so 0 and 1.5, so that'll be over here somewhere. So I'm going to connect those 2 points, and I get my first line. And I'll label it 1. Always draw your lines and label them. Now we're going to do the second one. The x-intercept is 3 halves and 0, so it's 1.5. That's right there. And the y-intercept is 0 and 6 fifths, I'm sorry. So it'll be 1.2. So it'll be somewhere here. Okay, so if I connect those 2 points, so I get that. Okay, so that's my second line. So my point of intersection is right here. Now if I had drawn these correctly, you would notice my point of intersection, the y value looks like it's 2 and the x value looks like it's 1. So this negative 1, so it looks like negative 1 and 2. So that's what it looks like in my case. Okay, so let's check this. Once we find the point of intersection, that is my solution, and we always write a solution as a point. Let's check this first to make sure it is the solution. So now if x is minus 1, we get negative 1 plus y is 2, so 2 times 2 is 4. Negative 1 plus 4 is 3, so that works. If x is negative 1, 4 times negative 1 is negative 4, plus 5 times 2, y is 2, so 5 times 2 is 10, so negative 4 plus 10 is 6. So it satisfies both of them, so this is my solution. Okay, so that's how we solve a system using graphing. And like I said, it is not a very good way to do that because if your numbers are not nice, you end up with decimals and things like that that don't repeat and things like that. It makes it really hard to graph those things correctly that keep repeating and so on. So that makes it hard to graph those things. The second way to solve a system is by substitution. The goal of substitution is what we want to do is we have a system that has 2 equations and 2 unknowns, right? We want to change it to an equation with just one unknown, one equation with one unknown. That's what we want to do. So we want to get rid of the 2. We want to make a system that has 2 equations and 2 unknowns into one equation with one unknown. That's what we want to do. So that's a goal of substitution. So how do we go about doing that? It's just two steps. So we pick any, and I'll capitalize the word any because it really doesn't matter. We pick any one of the equations and solve for any one of the unknowns. So that's a lot of freedom there. I have two equations, I can pick any one of those, and I have two unknowns, variables, so I can pick any one of those variables. It doesn't matter which one you pick. If you do the algebra correctly, you'll always get the same answer. The second step is substitute. That's where the word substitution comes from. Substitute the value of the variable, or the unknown of the variable in step 1 into the other equation. Okay, so for example, if I start with equation 1 in step 1, I would substitute the value into equation 2. If I had started with equation 2, then I would substitute into equation 1. So that's what this tells us. So now that we have our steps, let's take a look at how to solve its system using substitution. So we have x plus 2y is equal to 3, and we have 4x plus 5y is equal to 6. I'll label these. Always label your equations in a system since you have more than one. Okay. Now, it really doesn't matter which equation you pick and solve for which variable. But once you do enough problems, you'll notice that if you pick a certain equation and solve for a certain variable, you can minimize your work. Okay. But that doesn't mean if you hadn't picked that particular variable, you'll get the wrong answer. It just means you'll cut down the amount of work you have to do. For example, if I were to pick this second equation and solve for y, then what would I do? I would move the 4x to the other side, so I would end up with 6 minus 4x is equal to 5y. And then to solve for y, I would divide everything by 5. So clearly we generate fractions. Okay. On the other hand, if I pick the first equation and solve for x, all I have to do is move the 2y to the other side and I'm done. I have no fractions. So if you can avoid fractions, that's always a good thing. So let's do that. So we're going to pick one. We're going to pick equation 1 and solve for x. So if you write these things down, it'll help you, when you're looking back and referring back to these problems. So I'm going to pick equation 1 and solve for x. So I isolate x, so I get x is equal to 3 minus 2y. Now what do we do? What's the second step? We substitute, I'll abbreviate that SUB, substitute x into the second equation. The reason for that is because we started with the first one, so we always want to substitute in the second one. Don't substitute back in the same one, because that'll be going in circles. So then let's go ahead and do that. So equation 2 becomes what? Now wherever I see an x in equation 2, I'm going to replace it with this, because I'm going to substitute that with 3 minus 2y. So equation 2 has 4x, so it's going to be 4 times 3 minus 2y, and again the parentheses are important since I have two terms, so make sure you guys do that, plus 5y is equal to 6. Remember what I said at the beginning when we started substitution. Our goal is to make it into a problem of one equation with one unknown. So if you look at this problem now, I have one equation, just one unknown, and the degree is 1, so we know how to solve that, right? We want to isolate all the variable terms on one side, but before we can do that, we always get rid of the parentheses, right? So let's start by distributing. So we get 12 minus 8y plus 5y is equal to 6. I can add these guys up because they are the same y terms, so you get negative 3y. They have the same y term, and then we can move the 12 to the other side, so 6 minus 12 is negative 6. So I divide both sides by negative 3, so I get y is equal to 2. So we found the value of y. Okay, and that's the right value, because out here when we did by graphing, we found y was what? 2. So that's a good thing. Now how do I find x? Well, you don't have to do any extra work because we already know x. X is right here. What is x? It's 3 minus 2y from step 1. So to find x, you just basically use step 1. You can go back and this tells me x is equal to 3 minus 2 times 1. Okay, so that tells me 3 minus 2, so it gives me 1. So where did we mess up here? Because we messed up somewhere, correct? We had, y was 2, not 1. So there we go. Y is 2, right? So let me write this down so you can plug in a 2. So 3 minus 2 times 2 is 4, so 3 minus 2 is negative 1. So my solution is x is negative 1 and y is 2. And always go back and check your answers, and when you check your answers, please make sure that you substitute them into both the equations to check, not just one, because your solution should satisfy both of them. Okay, so now that we have a solution using substitution, this problem was easy because we were able to isolate x and get a value for x that didn't have fractions. So let me do one more problem where we end up with fractions, so you guys can see how to do that. So let's say if I have 2x minus 3y is equal to 6, and I have 4x plus 5y is equal to 7. So this is equation 1, equation 2. Okay, now it doesn't matter which equation you pick, you're going to get fractions in this case, correct? So let's just pick one and I'll solve. Let's pick be different. So let's pick 2 and solve for y. I'm just doing this to show you it really doesn't matter which one you pick and what you solve for. If you do the algebra correctly, it's all going to work out. So 2 becomes what? I want to solve for y, so I isolate the y term, so I get 5y is equal to 7 minus 4x, and then I divide everything by 5, so I get 7 over 5 minus 4 over 5x. So I know what y is now. Okay, so now what's the next step? We substitute y, we substitute the variable that we just found into the other equation. Since we started with 2, we're going to substitute y into 1. So let's do that. So what does 1 become? Well, wherever you see a y in 1, we're going to replace that value of y with this because we found y. So we get 2x minus 3 times y, so we get 7 over 5 minus 4 over 5x is equal to 6. So now we are down to one equation with one unknown. We just have x. Okay, so let's solve this. The first thing I would do is anytime it's a linear equation, we want to get rid of the parentheses, and the second thing you'll notice is I have fractions, so eventually I want to get rid of the fractions, and we do that by multiplying by the common denominator. You should be used to that. So we distribute the negative 3. Negative 3 times 7 is negative 21. Negative 3 times negative 4 is positive 12/5 x is equal to 6. And my common denominator here is 5, so I'm going to multiply each term by 5. So if you multiply this by 5, you just get 10x. If you multiply this by 5, this term here, the 5's will cancel, so you'll get minus 21. Plus, if you multiply this by 5, the 5's will cancel. 12x is equal to 6 times 5 is 30. So now we want to move all the variables on one side, numbers on the other side. So you get 10x plus 12x is 22x is equal to 51. Okay, so we get x is equal to 51 over 22. Okay, so we found x. Do I need to go through a lot of trouble to find y? Not really, because we already know what y is from up here. This is y. So this implies y is 7 over 5 minus 4 over 5 times 51 over 22. Okay, so let me reduce this. Since it's multiplication, I can cancel things from the top and bottom. 2 goes into that 2 times and into that 11 times. So I end up with 7 over 5 minus 102 over 55. Okay, so I need to add them. My common denominator here is 55. So I multiplied this by 11 and by 11. So I get 77 over 55 minus 102 over 55. Since they have the same denominator, I can add the numerator, correct? So if you do that, we get 20, we should get 25. Okay, so we get, and that can be reduced, so it becomes what? 5 over 11. So my answer is x is 51 over 22. We write our answer solutions as point, and y is 5 over 11. Okay, and like I said, you can always plug them back into the equation and see if they satisfy the equation. Okay, so keep that in mind. You can always go back and check your answers. Okay, alright. So let's go ahead and take a look at another problem, the other method. So we did two problems with substitution. I hope you guys follow. Let's take a look at the next method, which is elimination. So how do we do elimination? Basically, it's just a one-step process. What we want to do with elimination is we want to multiply either one or both the equations by some numbers. Now, I do want to stress this, and either one or both, and they don't have to be the same number. For example, I could multiply the first equation by 2 and the second equation by -7, or I could just multiply the first equation by 5. It doesn't matter. Either you can multiply one or both, but when you multiply both by some number, that number doesn't have to be the same. It could be two different numbers, one equation by one number, the second. That's why I put s in plural, and I hope you guys understand that. So you multiply either one or both equations by some numbers, so that when the two equations are added, one of the variables is eliminated. And that's where the name elimination comes from. Okay, so let's take a look at how to do this. Okay, we'll go back to our classic example that we've been working with. Okay, so let's say if I have x plus 2y is equal to 3, I'll call this equation 1. And we have 4x plus 5y is equal to 6. I'll call this equation 2. Okay, so now let's take a look at it. For example, let's say that I'm interested in getting rid of the x term. So when I add the two equations, x will go away. Well, then if this is 4x, this would have to be minus 4x for that to happen, correct? Because when I add them, -4 plus 4 will be 0. So I would multiply the first equation by -4. On the other hand, if I want to get rid of the y term, then what do I want to do? I want to make both of these y coefficients the same, except one positive and one negative, so that when I add them, they cancel each other. So how do I do that? Basically, I want to find the common denominator, okay, and make both of them the same as the common denominator. So for example, the common denominator of 2 and 5 is 10. So I want to make this a 10 and this a 10, except one will be a positive 10, the other one will be a negative 10. So when I add them up, the y's will cancel. So let's do that. I can do x easily, but I'm going to do y this time. So I'm going to take the first equation and multiply it by -5. Okay, so I get -5x minus 10y is equal to -15. I'm going to take the second equation and multiply it by 2. So I get 8x minus plus 10y is equal to 12. So now I'm going to add the two equations. When I add them, I add the x variables, I add the y variables, and the variables that don't have x and y. So when I add these, you add the coefficients. -5 plus 8 is 3x. When you add these, they will cancel because you have -10 plus 10 is 0, is equal to -3. So you divide both sides by 3, so you get x is equal to -1. So now how do you find the second variable? We just found one. So I should have written that down here and I didn't. So let me do that. It's not something I should have done that. You can still figure out how to find the variable, but let me write it down. So you substitute the value of the variable into any one of the equations to find the other variable. So we can substitute that value of x that we just found into any one of the original equations. I erased them, but you guys know that. I'm going to just substitute into 2. So I'm going to substitute into 2. So what is 2? If you recall, 2 was this. It was 4x plus 5y is equal to 6. So I'm going to replace x with minus 1. So you get 4 times negative 1 plus 5y is equal to 6. So we get negative 4 plus 5y is equal to 6. We get 5y is equal to 10. Because 6 plus 4, when you move the 4 over, it'll become positive. So you get y is equal to 2. So my solution is negative 1 and 2. So that's how we do elimination. If they don't specifically ask you to use a certain method, then always use elimination. That's always faster and works really nicely. But if they ask you to use a specific method, then please do so. Because later on, the reason why we're learning all these different methods is you'll notice later on that when we solve nonlinear systems, that means when the degree is anything other than 1, if it's nonlinear degree 2 or higher, then we want to solve those nonlinear system problems always with substitution. Okay, so that's why we studied substitution. And we studied elimination for just regular linear systems like the one I just did. It's just faster to use elimination. But substitution plays a key role because when we solve non-linear system in section 6.4, we will have to use substitution. Okay, so let's take a look at 2 special cases of linear systems. Okay, so the first case is what would have happened. Remember, we said the solution to a linear system is what? The point of intersection. What would happen if I graph the first equation, I got this, and if I graph the second equation and I got this? And you can clearly see these 2 lines are parallel. So do they have a point of intersection? No. So that means this problem, this system would have no solution. So if the graphs of the equation I'm sorry, let me write it better. If the lines are parallel, then the system of equations has no solution. So if the graph of the equations which happen to be lines are parallel, then that system has no solution. And how do we figure that out? Well, that always happens when you end up with something inconsistent. Anytime you're solving a system, doesn't matter what method you're using, and you end up with something inconsistent, then we say that that system has no solution. And by that I mean something like the 0 is equal to some number. Is 0 equal to a number? No. So that tells me that that makes no sense. So that must be inconsistent. So that means that system has no solution. So it doesn't matter what method you're using, substitution or elimination, if you end up with something inconsistent, then right away you know you have no solution. The second thing to note is, let's say that I have a system and I graph the first line. Okay, I end up with this. So this is the graph of the first line. Then I graph the second line and I end up with this. So how many places do those 2 lines intersect? They actually intersect at every single point. So in this case, this system actually has infinite solutions. Okay, so if the 2 lines are the same, if the graphs of the 2 lines are the same, then the system has infinite solutions. Okay, now how do we capture that? How do we know a system has infinite solutions? Let's say you're solving and you end up with 0 is equal to 0. So then right away you know your system has infinite solutions, because 0 is equal to 0 is always true. And it makes sense that you will end up with 0 is equal to 0. So let me show you with this example up here. Okay, let's just say for the sake of argument, this problem was this. Okay, I had 4x plus 6y is equal to 12 minus 6y. Okay, I had this instead of the one I had before. Now you can clearly see if I multiply the top equation by 2, by negative 2, you end up with what? Negative 2x plus, negative 4x plus 6y is equal to negative 12, and you don't do anything to the second equation. So we get 4x minus 6y is equal to 12. So let's add them. This will cancel, this will cancel. Okay, and so does this. So we get 0 on the left is equal to 0. So if the two lines are the same, anytime you add them up, since you're multiplying one by a negative to eliminate one of the variables, so when you add them up, everything gets eliminated. So in that case, we get infinite solutions. Okay, so let me go ahead and give you examples of both of these special cases, and I'll do one with substitution and one with elimination, so you guys can see some more examples of each of those methods. Okay, so let's take a look at this. So we have let's say we have a system like this. We have 3x plus 6y is equal to 11, and we have 2x plus 4y is equal to 9. Okay, I'm going to solve this by elimination. Okay, so I'm going to eliminate x. I'm going to multiply the first equation by negative 2, because the common denominator of 2 and 3 is 6. Okay, so I want to make both of these 6's, except one positive 6 and one negative 6. So I'm going to multiply the top one by negative 2 and the bottom one by 3. Or I could have done the top one by 2 and the bottom one by negative 3. You have to have one negative and one positive. So this tells me I have negative 6x minus 12y is equal to negative 22. And the second equation we're going to multiply by 3. So we get 6x plus 12y is equal to 27. So let's add them. If you have a positive 6x, negative 6x, that cancels. You have negative 12, positive 12, that cancels. So we get 0 on the left. Negative 22 plus 27 is 5. Is 0 equal to 5? No, it's inconsistent. Okay, so that tells me that this system has no solution. Okay, so just keep that in mind. Alright, so now that we know that, let's take a look at a system that has infinite solutions, and we'll solve this using substitution. Okay, so let's find a system that has infinite solutions. Let's see, we have 4x plus y is equal to 2, and you have 8x plus 2y is equal to 4. So this is 1 and 2. I can solve this by elimination, but I'm going to do substitution here. So always try to avoid fractions if you can, and sometimes you just cannot, but you should always try. So I'm going to pick 1 and solve for y. Pick 1, equation 1, and solve for y. So what does 1 become? I want to isolate y, so I'm going to move the 4x to the right, so I get y is equal to 2 minus 4x. Then we're going to substitute y into the second equation, into 2. So So the second equation becomes this. I have 8x plus 2y. But what is y? 2 minus 4x is equal to 4. So now we distribute and solve. So we get 8x plus 4 minus 8x is equal to 4. So we get 8x minus 8x is equal to 4 minus 4. We're just solving a linear equation. On the left I have 0, on the right I have 0. Okay. So now how do I find x and y? Because this tells me what I have infinite, because x 0 is equal to 0 is always true, correct? But you do want to find those infinite solutions. So now at this stage, anytime you have a 2 by 2 system, to find the infinite solutions, you can take one of the variables and set it equal to a constant. A constant is any real number. Okay. So in this case, I always prefer to do that with y for a 2 by 2 system. So I'm going to say in this case we were trying to solve for x, right? So let's set x to some constant c, where c is a constant, which implies any real number in this case. Okay. Now the reason why I set x to a constant, because I was solving for x, so I set that to a constant because there was no way to solve for x. So now what is y then? That's right here. Remember, step 1 gives you y, so this implies y is what? 2 minus 4x. So if x is c, so it'll be 2 minus 4 times c. 4x. So we get 2 minus 4c. So that's what y is. So my solution is x is c and y is 2 minus 4c. So there's my solution. Okay. Now if you were solving this by elimination, it really doesn't matter what you call c. You can call one c and then you can find the other one by substituting whichever one you call c into one of the original equations. Okay. Now why is this called infinite solutions? Well, c is any real number, so for different values of c's you're going to get different solutions. For example, if c is 0, my solution would be 0 and 2, because 4 times 0 is that. On the other hand, if c is 1, my solution would be 1 and 4 times c1 is 1, so 2 minus 4 is negative 2. If c is negative 3, my solution would be negative 3 and 4 minus negative 4 times negative 3 is positive 12, plus 2 is 14. Or I could even have fractions. I could pick 3/4. If c is 3/4, I get 3/4, and then I get 2 minus 4 times 3/4. You can see that the 4's will cancel, so you get 2 minus 3, which is minus 1. Okay. So basically c can be any number, so you can clearly see you're generating infinite solutions. So that's how we solve a system of 2 equations and 2 unknowns using graphing, substitution, and elimination. Before I end this section, let me just do one problem that's a little bit different, not too different than the ones I just worked with. Something like this. Let's say if I have 5 over 6x minus 1/3 y is equal to negative 6, 1/6 x plus 2/3 y is equal to 1. So I want to solve this system. Okay. Now you can solve the system the way it is. Like for example, I can multiply the first equation by 2, and if I do that, this will become a 2, and when I add them, these will cancel. But what if it wasn't as simple as that, this problem? Then what would you do? The first thing you always do is, whenever you're solving, is get rid of the fraction. So in the first case, the common denominator is 6. I would multiply everything by 6, and in the second case, the common denominator is also 6. It doesn't have to be the same. Like for the first equation, the common denominator could be 6, and the second equation it could be 4. But basically is you want to multiply by the common denominator to get rid of the fraction, as that's what you want to do. Okay, so keep that in mind. So the first equation I'll multiply by 6, so I get 6 times 6 is the 6 will cancel, so that just gives me 5x. If you multiply this by 6, you'll have a 6 here. 3 goes into 6 2 times, so you'll get negative 2y, and 6 times negative 6 is negative 36. So that's my first equation. If I multiply the second one by 6, you get 1/6 times 6 is just x, plus if I multiply 6 by 2/3, so 3 goes into 6 2 times, you get 2 times 2 is 4y is equal to 6. That's my second equation. So now I'm working with this system as opposed to this one that was pretty ugly. So now let's do this. Let's find a solution. So how do? I want to get rid of the x, so I'm going to leave the first equation alone. So I get 5x minus 2y is equal to negative 36. But the second equation I'm going to multiply by minus 5. So I get negative 5x minus 20y is equal to negative 30. Okay, so when you add them up, this cancels. Okay, so you get negative 22y is equal to negative 66. So if you divide by negative 22, you get y is equal to 3. Okay. Once we find y, to find x, it's easy. You can take this y value and plug it into any one of these. Doesn't matter which one. I'm not going to plug it into the ones with fractions because I got rid of the fractions and got these two that are easier. So I'm going to plug it into 2. Okay, so the second equation tells me what? I have x plus 4y is equal to 6. So we have x plus y is 3. So 4 times 3 is 12 is equal to 6. We get x is equal to negative 6. So my solution is negative 6 and 3. So if you do have fractions, try to get rid of them, especially when you're doing elimination. And even if you're not doing elimination, when you're doing substitution, you can try to get rid of the fractions and then do the substitution if you feel comfortable. Okay.